All right, hi guys, Mrs. Rona here. We've been talking a lot in this unit so far about what happens when torque, the net torque acting on something, is equal to 0. So when the net torque 0, things are in equilibrium. But what happens if net torque is not equal to 0? What happens then? And what happens is, as we've kind of noticed, things start to rotate. And so in this unit, we'll be discussing objects that are rotating. We need to be familiar with angle measurements in radians, and things, angular speeds in radians per second. We'll talk about angular acceleration. So we need to make sure we're all good on radians. So first of all, we've got a circle here, if you remember your unit circle. And if you look at this bar, if we were to sweep this bar out, we could make different angles in this circle. So real quick, let's remind ourselves of the conversion factor. 2 pi radians, that's one circle. So that's 360 degrees. That's if this bar went all the way around, came back to here, it would have gone around 2 pi radians. So anytime something makes one full circle, it's 2 pi radians. So if we look at that, we can figure out how many degrees 1 radian is. Well, the conversion is if you take your amount of degrees and you multiply it by pi over 180, or any factor where you have the number of radians divided by the degrees, that's going to tell you how many radians you have. So 1 radian is actually 57 degrees. That would be about an angle of right about there. So this angle right here would be 1 radian. So let's assume a metal bar, so that metal bar here we were looking at, this black bar, rotates counterclockwise through an angle of 1 radian. Draw where it ends up and label the angle it swept out. That's what I just did. So this bar starts here, swings up to here. That would be it rotating through 1 radian. Question number 4, the object starts back at its original position and rotates 2 radians. So that would be about twice that angle. So I'm going to go over here. Okay, maybe I'll make this one in blue. Okay, so 2 radians would be if we did this. That's 2 radians. Number 5, an object spins counterclockwise at 3 radians per second. Draw and label the angle it sweeps out after 2 seconds. Well, if I'm going 3 radians per second times for 2 seconds, I'm going to go through 6 radians. 6 radians is almost a full circle, because a full circle is 2 pi. Pi is 3.14. So if I go through a circle of 6 radians, I'm almost going to make it back around. It's probably going to be an angle right about here. That's going to be 6 radians. Okay, so if something rotates 6 radians, it goes almost all the way around. So let's think back to playing Crack the Whip. That was when the 4 people stood next to each other and we spun around as fast as we could in a circle. So this first question says, if the person in the third ring, the outermost person, makes 1 full revolution, what distance do they travel? So if we look at the distance that they travel, that's going to be the circumference, and we know that that is equal to 2 pi times the radius of the circle. We did that the other day. Not the other day, back when we did Crack the Whip. So what about if we wanted to figure out the distance that this first person in the first ring traveled? Well, then we would do their circumference would be 2 pi times a shorter radius, so 1/3 the radius. So that's just the distances they travel. Distance would mean how many meters did they go if they walked that full circle. So question number 2 says, if the person in the outer ring makes 1 full revolution, what angle do they sweep out? So if this person goes all the way around the circle and comes back to where they started, they've rotated around 2 pi radians, right, or 360 degrees. If we look at the person in the first circle, if they go all the way around in a circle, they've also swept through 2 pi radians, or 360 degrees. Question number 3 says, which person has the largest tangential speed? So tangential speed would be, remember, this person has a speed tangent to the circle. We drew it like that. So this would be the V tangential. So their tangential speed is just going to be distance over time. So we look at the velocity would be the distance divided by the time. Well, who traveled more distance? definitely the person in the outside of the circle. So the outside person travels more distance in the same amount of time. This other question asks the logger's angular speed. So angular speed is how many radians you go through each second. So angular speed is how many degrees or radians, let's call it your angle, divided by time. And that would be the same for both, because they both sweep out 2 pi radians in the same amount of time. So they'd have the same angular speed, even though the person on the outside has a greater tangential speed. Question number 4, how would you calculate the translational distance a person traveled at a radius r traveled through any angle theta? So we want to know translational distance. So I like to think of that as circumference. So we know circumference for a full circle is 2 pi r. But they're saying, let's say they don't go through a full circle. They just go through an angle theta. Well, a full circle, the angle is 2 pi. So the distance you travel if you're going in a circle would just be theta times r. Full circle's 2 pi, that's 1 full. If we're just going part of a circle, we'd take whatever angle we go through times the radius. How would you calculate translational speed of a person running at a radius r through any angle over some amount of time t? Well, if the distance from number 4 is theta over r, we know speed is distance over time. So we could just do theta r divided by time. Could tell me how fast someone's going. Number 6, how would I calculate their angular speed of a person running through any angle theta over some amount of time? Angular speed, like we said above, is just how many angles you go through over a certain amount of time. So I would just say their change in their theta divided by time would give you some angular speed. What are 3 ways to accelerate? So this is just normal translational acceleration, forward or backwards. You could speed up. You could slow down. And the one people always forget is you could just change direction. So if you're changing your direction but moving at a constant speed, you're undergoing acceleration. Then number 8, what are 2 ways to experience angular acceleration? Well, that would be to rotate faster or rotate slower. You can't change your rotational direction because you're already changing direction when you go in a circle. So it's rotate faster, rotate slower. Okay, so just like we had kinematic equations back in Unit 1, we have rotational kinematic equations in Unit 6. So I'm going to kind of show you the translational motion. So this is Unit 1 stuff. So forward, backward, up, down, right, left, and rotational motion, which is Unit 6, and kind of how they relate, and then what the symbols, what's the analogy, what's the translational analogy to the rotational. So if we talk about displacement, the symbol we used was delta x for translational motion, and that was, the definition we used was the straight line that you traveled through. So basically it was distance, the vector version of distance. The units we measured that in was meters, and we said you could either have a positive displacement or you could have a negative displacement. So in rotation, instead of displacement delta x, we have your change in theta, delta theta. How much angle have you gone through? So the definition is the angle that you've rotated through. The units are radians, and the direction can be also positive or negative, but this would not be right, left, up, down. Positive would be counterclockwise, negative we would consider clockwise. So how can they relate? If I know something went through a certain displacement in a circle, how can I figure out what angle it went to? Well, the distance that you've rotated through is equal to theta times r. We derived this on the other page. Kind of a more convenient way to think it through is that the distance divided by the radius is equal to the angle swept through. So that's kind of the conversion from translational to rotational. All right, let's talk about velocity. Unit 1, our symbol we used for velocity was V. Oops, sorry, let me make that prettier. Was V. The definition was the change in distance over time, or the displacement over time. Units would be meters per second, and again, you could have a positive or a negative velocity. So in Unit 6, we're going to talk about angular velocity. So the symbol is an omega. It's kind of a curly W. It's a Greek letter, omega, lowercase omega. The definition is the change in theta over time. How much has your angle changed over time? The units for angular velocity are radians per second. And just like above, you can have positive or negative, but what that means is counterclockwise or clockwise. The conversion looks just the same as above. Your translational velocity is equal to your rotational velocity times the radius. Or more commonly, we'll probably use the velocity divided by the radius is equal to angular velocity or angular speed. And last but not least, we've got acceleration. So in Unit 1, we use the symbol A for acceleration. We defined it as any change in velocity over time. So that gave us the units of meters per second, or meters per second squared. And we said we could have positive or negative acceleration. So the rotational version of that is rotational acceleration or angular acceleration. We use an alpha, okay, the Greek letter alpha for that one, so kind of like that infinity sign without the right side. The definition is a change in angular speed over time. The units are going to be radians per second, or radians per second squared. And the direction can be positive or negative, but that means a counterclockwise acceleration or a clockwise acceleration. The conversion between the two, how do they relate? Acceleration translationally is equal to rotational or angular acceleration times radius. Again, more commonly, we'll probably use that acceleration over r is equal to angular acceleration. And so now we have our kinematic equations from first semester. So if you remember these, we have x final is equal to x initial plus initial velocity time plus 1/2 at squared. We also have v final equals v initial plus acceleration times time. And our third one was v final squared equals v initial squared plus 2a times the displacement. Now for every single one of those translational kinematic equations, we have a rotational kinematic equations. So all you're going to do is when you see an x, place a theta. Where you see a v, you'll place an omega for angular speed. And every time you see an a, you'll put an alpha. So that first equation is theta final equals theta initial plus omega initial t plus 1/2 alpha time squared. These are all on your equation sheet as well. Second one would be omega final, so final angular speed is equal to omega initial plus alpha t. And the last one is omega final squared equals omega initial squared plus 2 alpha theta final minus theta initial. So these become our rotational kinematic equations. So we'll practice with more of those tomorrow. Thank you for watching. Have a fabulous day.